Unit 4 is going to take us beyond our solar system to explore stars and galaxies. But before we do that, we might as well study the star that's closest to us. This is the beginning of Unit 4A, and in this lesson we're going to look at the Sun. Here are the Unit 4A learning outcomes. Pause the video and write these in your notes. So how do we study the Sun anyway? We can't use normal telescopes, but we use what's called solar telescopes. And here's an example. The sunlight comes in and is bounced off a series of mirrors so that an image, such as this over here, can be studied safely and in detail. Stars are made of something called plasma. So what is plasma? Well, it's considered to be the fourth state of matter. We have gas, liquid, solid, and then we have plasma. It's an unusual type of material that consists of ionized atoms. In other words, the hydrogen and helium in the Sun has been stripped away of its electrons. The reason is because of the high temperatures in the Sun and all stars. All stars are made of plasma. We're going to investigate the Sun from the inside out. We'll start with the interior and move our way to the photosphere, the chromosphere, and the corona. Just to give you an idea for temperatures, the Sun's interior is estimated to be about 15 million degrees. The surface of the Sun, which is the photosphere, is estimated to be at about 6,000 degrees. The corona, which is the outermost layer, heats up again to about 1,000,000 degrees. So let's start with the Sun's interior. Go ahead and pause and draw 3 circles like I've shown here. The innermost circle is the core, and this is made of helium. The next layer is called the radiation zone. The radiation zone radiates energy that's produced in the core. Now, how is that energy produced? Well, the Sun undergoes something called nuclear fusion, and this is where hydrogen atoms undergo a nuclear reaction that produces helium. Here's a simplified way to look at that equation. Hydrogen goes to helium. But it also gives some energy, and that energy is what we feel, the heat of the Sun. So this happens right here between the core and the radiation zone. Hydrogen turns into helium. So given those circumstances, what's happening to the size of the Sun's core over time? If you said it's getting bigger, you're correct. Hydrogen is disappearing and producing helium, which is making the core larger and larger over time. The next layer is the convection zone, which is also made of hydrogen. Here we have the energy from the core and the nuclear fusion reactions moving outwards, but in this case, it's moving in convection fashion instead of direct radiation. The next part of the Sun we'll look at is the surface, or the photosphere. There really isn't a surface, of course, because the Sun is a big ball of gas. So you can just highlight the outer part of this circle and call it the photosphere. The photosphere has a grainy appearance, which you can see in this picture right here. That is the result of convection. Where material is moving upwards in the convective zone, it gives a bright color at the surface. And where it's moving downwards, it's a bit cooler, so it makes a darker looking color. So the graininess is the result of the underlying convection. Here's a summary of some of the features of the photosphere. The granulation, which I just mentioned. Sunspots, which you looked at in an assignment, are dark blemishes that are strongly magnetized. Prominences are these huge arch-like explosions of gas and plasma. And then solar flares are events that are extremely intense. They last 1 or 2 hours and they shoot plasma out from the Sun. When solar flares interact with Earth's magnetic field, we get auroras. In the northern hemisphere, they're called aurora borealis, or the northern lights. Here's a picture of a prominence. Here are some sunspots. Here's a close-up of some sunspots. Sunspots are actually several thousand degrees cooler than the surrounding Sun. They're highly magnetized and they always occur in pairs. Here's another solar prominence, and here's the Earth for scale. We're about the size of one of these granules. Here's some auroras that are produced when solar flares reach the Earth's upper atmosphere. And here's another one that occurred in 2012. A CME is a coronal mass ejection. It's just another kind of explosion of material from the sun's surface. Above the photosphere, we have the first layer of the atmosphere, if you want to call it atmosphere, called the chromosphere. And this consists of narrow jets of rising material. So I've kind of illustrated it here with little jets of material above the photosphere. Here's an actual picture of the spicules of the chromosphere. Looks almost like feathers. Finally, the last layer is the corona, and I've made the sun smaller here so that I can put the corona more to scale. It's very, very large. It extends very far from the sun's surface, and it produces the solar wind. The solar wind is a high-speed stream of particles going in all directions, and the speed is extremely fast, 500 kilometers a second or 300 miles a second. And remember, the Earth's magnetic field protects us from the solar wind. Here's the corona, which is best seen during solar eclipses. Here's another example. Finally, I want to just mention something about the sunspot cycle. You did an exercise about this and you graphed some of the more recent cycles. Ever since Galileo first looked at sunspots, we've been counting the solar cycles. In 2020, we've entered solar cycle 25, and it is expected to peak in the year 2025. On the bottom here, I have the entire history of solar cycles since 1750, when Galileo first noticed them with his telescope. You can see that there is somewhat of a pattern, and it's an 11-year pattern. Every 11 years we have a peak, and then a trough, and then another peak. And that's a cycle, 11 years, peak to peak. Astronomers who study sunspots believe they are related to a flipping of the sun's magnetic field every 11 years. Because the sun is not solid, it doesn't rotate as a whole like the Earth does. It does rotate, but the equator of the sun rotates faster than the poles. What happens is the magnetic field that's generated is sort of stretched and tweaked and interacts in a strange way compared to how our magnetic field interacts. And it's related to the production of the sunspots. This is just a reminder that your textbook has pictures of the sketches we just drew and information that reinforces what I've described. Coming up next, what is light?